Alright, okay. I think we left off at parser. Alright, let's get started. Everyone who has ever programmed has probably heard about parsers, mostly about by encountering a parser error, or maybe heard or even said something like, we need to parse this. After it's parsed, the parser blows up with this input. The word parser is as common as compiler, interpreter, and programming language. Everyone knows that parser exists. They have to, right? Because who else would be responsible for parser error? Okay. Takes input, frequently text, and builds a data structure, often some kind of parse tree, AST, or other hierarchical structure. JSON parser isn't the same as a parser for programming language. They're different. I can see where you're coming from, but no, they are not different. At least not on a conceptual level. A JSON parser takes text as input and builds a data structure that represents the input. That's exactly what a parser of a programming language does. The difference is that in the case of JSON parser, you can see the data structure when looking at the input. Whereas if you look at this, it's not immediately obvious how this could be represented with a data structure. This is why, at least for me, they seem different on a deeper conceptual level. In most interpreter and compiler, the data structure used for internal representation of the source code is called a syntax tree. Okay, so the internal representation of the source code is a AST. Let's say we have the following source code, and let's say we are using JavaScript, have a magic lexer, a magic parser, and the AST is built out of JavaScript object. Then parsing step might produce something like this: type, condition, type, operator, left, operator, left, right. Okay. The AST is pretty abstract. Produce a data structure which represents this source code. Why not a parser generator? I heard about the parser generation like tools like Yak, Bison, or Antler. Parser generator, a tool that when fed a formal description of a language produce. Interesting. Oh wow, this parser generator. And the majority of them use a context-free grammar as their input. Makes sense. Writing a parser for the monkey programming language. There are two main strategies when parsing a programming language: top-down parsing or bottom-up parsing. Recursive descent parser. constructing root node of the AST and then descends, while the latter does it the other way around. A recursive descent parser, which works from the top down, is often recommended for newcomers parsing, since it closely mirrors the way we think about ASTs and their construction. I personally found the recursive approach starting at the root node really nice, even though it took writing some code before the concept really clicked, which is another reason to get started with the code instead of delving into parsing strategies. Now, when writing a parser ourselves, we have to make some trade-offs. Yes, our parser won't be the fastest of all time. We won't have formal proof of its correctness or its error recovery process, and detection of erroneous syntax won't be bulletproof. The last one is especially hard to get right without extensive study of the theory surrounding parsing. Okay. Parsing let statements. Okay, this is the most simple. Bind a value to a given name. So you bind a value to a given let x. You bind 5 to x. Not trying to parse correctly. What does that mean? The parse means the parser produces an AST that accurately represents the information contained in the original let statement. That sounds reasonable, but we don't have an AST yet, nor do we know what it should look like. So our first task is to take a close look at monkey source code and see how it's constructed so that we can define the necessary parts of an AST that's able to accurately represent let statement. Okay. A let statement in the monkey consists of two changing parts, an identifier and an expression. In the example shown above, x, y, and add are identifiers, 10 and 15, and the function literal are expression. Okay. That go. Packet AST type node face token literal string type statement in face node statement node type expression interface. So node expression node. Okay, here we have three interfaces called node, statement, and expression. Every node in our AST has to implement the node interface, meaning it has to provide a token literal. So node, statement, expression. Every node in our AST has to implement a node interface, meaning it has to provide a token literal, meaning what it is. Return the literal value. But always used for debugging. The AST we are going to construct consists of solely of nodes that are connected to each other. Okay, so I see, that makes sense. So to connect to each other, some of these nodes implement the statement, and some the expression interface. These interfaces only contain dummy methods called statement node and expression node respectively. They are not strictly necessary, but it helps us by guiding the Go compiler and possibly causing a throw error statement. Okay. Type program struct statements. So this is the program, program. So it's a struct that has statement. Okay. If length key statements. the programming node is going to be a root node of everything. So series of statement makes sense. So each line, pretty much. No, not necessarily, but statement. Okay. Type let statement struct token name identifier value expression following as let statement. So this is a struct implement node. Identifier import monkey token identifier expression node. Oh crap. The let statement has fields we need. Name to hold the identifier of the binding value. List of statement, let statement, it has identifier and expression. Let's see, so identifier, expression. Monkey AST. Oh, parser.go. Oops. Parser. I don't have parser yet. Parser.go. Okay. Packet parser. Import monkey AST monkey lexer monkey token type parser struct. It has a lexer in it and cur token p token and then it has a new function lexer. parser p parser return nil. Alright, the parse has three fields: lexer, current token, peak token. L to an instance of the lexer, which we repeatedly call next token to get the next token of input. So that's the lexer parser. Cut token. Alexa's position. Alexa's position. They point to current and the next token. Both are important. We need to look at the current token, which is the current token under examination, to decide what to do next. We also need peak token for this decision. If current token doesn't give us enough information, think of a single line only containing 5. Then current token is a token in, and we need peak token to decide whether we are at the end of the line or if we are at the start. I see. Okay, parse program, new program, advanced token until the token is not the end of line. If current token is let, parse let statement. Okay, if it's return, parse return statement. Okay, I see. So keep push the statement into the program.statement and advanced tokens. I see. So you just go to the next line, I'm assuming. I see. So let's say you expect a equal sign. Since this is pseudocode, there are a lot of omission, of course, but the basic idea behind recursive descent parsing is there. Password node and able to shout out stand by calling other functions. Parse 5 plus, then call. Alright, let's write this test and then call it a day. Parser test.go package parser import testing monkey ast monkey lexer func test let statements t testing.t input let x equal 5, let y equal 10, let foo bar equal 83838 838383. Okay, cool. lexer.new input, put that into lexer p, and then we create a program with the lexer program p.parse program, parse program equal nil. Then we're gonna log it out. Parse program return nil. If length program dot statement not equal to 3, t dot fatal. If program dot statements does not contain 3 statements, got length program dot statements. Struct expected identifier string. Okay. For ITT range plus statement. Statements. If test that statement, t statement, t not expected identifier return. Okay. Why doesn't I feel like I'm having a little bit too many. Why do I have so many? Oh, I put it inside of it. Test that statement. Test.ts. And t statement. Name string bool. If s token literal, let token literal percent q s dot token literal returns false. That statement. That's not. Huh? All right, I think we at a good stopping point. Cool. So we just add test failing. Alright, cool.